Good morning, track two. Welcome back for those that left. Here we have about to start up Mr. George Simonds. He's going to give an awesome talk about the new cyber engineer, how immersive learning shapes solution engineering at industrial facilities. And again, please remember to purchase some merch and join us at Discord. Without further ado, George, I'll hand it over to you.
Awesome. Well, good morning, everybody. Here I'm going to share my screen with you guys so that you can see the presentation. I kind of feel like Mr. Rogers a little bit, being able to sit in a chair and also do a presentation at the same time. So anyway, it's good to be here this morning. As the second time being able to join you at CornCon. I love these conferences. They have to be the most creative I've ever attended. I wanted to talk a little bit today about what I call the new cyber engineer. And what that really means are engineers that are working and performing job functions at industrial facilities, and really how we use immersive learning to kind of shape the way they engineer solutions in these really kind of difficult or challenging environments. So a little bit about ICIS. It's a 501c6, it's a nonprofit, and what we specialize in is workforce development and really research as well in cybersecurity and critical infrastructure. And that's a lot, I know, to put in one sentence or what have you, but the truth is we really need a way in order to do this cross-disciplinary approach between cyber and the engineering disciplines in terms of how we carry out cyber-based programs in these types of facilities. And to give you an example, over on the right, that's a picture of really a small modular reactor, a small nuclear reactor that's a part of our lab. And what you see in there is you might be able to tell there's some wiring and whatnot going on, but there's a lot of digital components inside of this particular lab that's a little bit different from what you'll see in a traditional IT environment. And also, it gets a bit confusing because unlike walking into a traditional data center, you're walking into a power plant or a large industrial space. So how this stuff works and how you come together as a team to make sure it's protected from cyber-based threats is just very different. So how do we get to a place where individuals who are trained or otherwise interested in a cyber career learn how to apply their skills in a place like this? So a lot of ways I think about cybersecurity as a whole and as a discipline, I would think, if I were sick or ill, where would I want to go in order to seek treatment? And what if I went back in time to like the 19th century? And if I had a choice between getting healthcare in the 19th century to getting healthcare in today's modern age, which would I choose? And some of these pictures here are kind of a graphic to kind of give you an idea of what it was like back in the 19th century. And some describe it as somewhat barbaric. But really, as a society and as a culture, we really didn't have a whole lot of innovation, or we were still in the learning process about how to implement these disciplines in ways that promoted good health care or patient safety or what have you. I'll give you an idea there. So think about this. The first hospital was actually established in the United States in 1751. This was in Philadelphia. It was called the Philadelphia Hospital. So that's 1751. That's almost a little over 250 years ago or what have you. But when we get into 100 years ahead of that, in the mid-19th century or so, they said, according to the Washington Post, the chances of post-surgery survival were so low that hospitals often force patients to pay up front. So imagine that. Imagine if you're going in for a routine procedure or you have some sort of emergency and the doctors are saying, I need you to pay up front because there's no way I can guarantee you're going to come out of this in good shape. And also at the time, even more interestingly, they weren't really sure how to do something as simple as blood transfusions. they actually believed at that time that you could use milk as a way to transfuse or to transfuse blood in order to save sick patients. So there was a brief in what they call bizarre time in the late 19th centuries when they were convinced that milk was the perfect substitute for lost blood. And that's pretty interesting in many ways. So if you think about that from a cyber discipline, we're not that far off in terms of it's relatively a new discipline. And when you think about where technology has come over the past 20 or 30 years, we're still at a place where we're trying to figure out how exactly do we go about implementing protective measures and defensive strategies in ways that really work. So in a lot of ways, we're experimenting and we're trying to figure out what would work best. So let's take a look at that. So you may be familiar with NIST, the National Institute of Standards and Technology, and they have what's called the 800 series publications. And many of you may already be aware of that, but back in 2005, they published this thing called the 853. And what that was is a catalog of security controls and a methodology to implement them that essentially said, here's all the things you should do or think about to protect an asset or to protect a digital device. Around the same time, and there was another publication called the 882, which was essentially a way of taking 853, all these security controls, and applying them in an industrial environment. So the 882, the idea that we could actually protect industrial control systems while not new, codifying it and putting a formal guideline in place started around the same time as all this emphasis on federal IT systems and DoD systems. So in the end, the draft of the 882, starting sometime in 2005 and 2006, it would be almost a half dozen years later before the first iteration comes out. That's 6 or so years after the 853 came out. It took a while to figure out what is the best way to take these best practices and implement them in an industrial facility. And skipping ahead, the last revision of that was in 2015, whereas the 853 for federal systems was just revised here recently in 2020. And the 882 for industrial focus is also in process. It's always in a process of being updated, but it kind of gives you an idea of what I would call the cyber lag. And really what that has to deal with is that when we start talking about applying cybersecurity in these industrial environments, it's actually a little bit harder. And there's a reason for that, which we're going to talk about. But the idea that we are trying as an industry to improve and mature, we're kind of in this interesting time when we get to witness it and be a part of it. Just like back in the 19th century, whenever doctors and practitioners were trying to hone their skills and improve patient care, we're at a place where we have an opportunity to do the same thing. We're not healing people, but we're certainly protecting and playing an important role in protecting the nation's critical infrastructure, especially understanding how digitized that infrastructure really is. So I'll give you an example here. So we call it a soft gooey center with a hard outer shell. I mean, everyone growing up has probably had experience with a gobstopper. I mean, this is something you give to a kid and they essentially are, busy for at least a half an hour or more. Well, a gobstopper is very similar to what we would call the Purdue model for industrial automation. And what that means is over time, over the past 30 to 40 years or so, we've seen more and more automation in industrial environments. But keep in mind, the types of automation, the types of digitization have not necessarily kept in pace from a security perspective. And so if you break a plant or a manufacturing facility or whatnot down, there's really about 5 different levels to the architecture as a whole. At the highest level, you have the enterprise networks. This is where your business systems are and your email systems and the things that you're kind of accustomed to for day-to-day work activities. But as you drill down, all the way down to level 0, you have these industrial automation components, industrial control systems, SCADA architectures, things that are very different from traditional IT that are running critical processes in a plant. These are things that can be making decisions that have a massive impact on the plant's ability to function. And in some cases, in the worst case scenario, you're talking about pieces of equipment that are making decisions that could have impacts on everything from human life to environmental concerns. When we have massive pipes that are pumping, thousands of gallons of water at a time, superheated infrastructure, caustic materials, all these things that are happening at once, you really want to make sure that that technology is doing what it's supposed to be doing. And the main emphasis as a result is that it basically be designed and implemented with the highest levels of functional integrity. And so all these other features and functions in this technology that would otherwise equate to, things that a user might like more, or even security, were kept out because they didn't want to introduce complexity into the architecture, because that means that we would be more likely to have a failure mode or a failure state that would be unpredictable. And so as you drill down into that process layer, we have a lot of simple, what we call non-native components, meaning they don't have any native capability to actually protect themselves. And when we talk about the timelines here, about when NIST was publishing and putting out these guidelines, I'll give you an example. So back in 2001, after 9/11, we had a series of regulations and requirements that got pushed out to the nuclear power industry. And between 2001 and 2006, really that was what we would call risk-based, meaning someone got to make a decision as to whether the risk was significant enough to actually take action. And what the regulator found in 2006 is that everyone just basically considered there to be very little to no risk, which wasn't actually the case. And so in 2009, they actually came out and said, well, we're actually going to formalize a regulation and make it a requirement. So there isn't a choice. We're going to take risk out of the equation and make sure that everyone's doing these things. But it took from 2009 to today to really begin maturing it. And what that means is that even though we knew there was a problem at the turn of the century, it's taken almost 20 years to get an industry at the place where they're formally adopting these, these more capable cyber solutions and what have you, pushing what we call situational awareness for cyber security deeper and deeper into the plant where these industrial control components are operating. So why is that? Why did it take so long? Well, that's where we come to the multidisciplinary expert. Really, the issue that we face is that when you get into the plant and you have to start introducing cyber technologies, what you find is a certain level of disruption. Most of the equipment in a plant is what we call run to failure. It means you install it or you implement it, and then you only touch it maybe in 2 to 3 year cycles during when a plant shut down, or it doesn't undergo regular patch management. And in some cases, this equipment is really old. I wish I could show you guys pictures of some of the stuff that we've seen when we're out there doing evaluations at these plants. We're talking about technologies that are, for which the vendors have gone out of business, a decade ago. We're talking about, in one case, I had the pleasure of seeing probably something that should belong in a museum, but it was a hard drive that was about the size of a bureau or a sofa that had these large platters that were probably, as big as my fireplace. But this stuff has just been there for a long, long time. but it's one of those, if it works and it's not broken, then you don't touch it and you keep moving forward. They'll pull people out of retirement to come in and actually maintain these systems. If you want to get access to some of the systems, you actually have to get permission from about 4 different layers of engineering approval just to open a cabinet. And if you open the cabinet, you can't break the plane, which means you can't actually reach your hand into the cabinet or shine a flashlight into it because the equipment can be so sensitive. So that's why it takes so long, because the amount of planning and strategic planning, really, to get in there and actually do this type of work or put cyber into these spaces really just takes time. And that's because over to the left, you'll see there's so many different types of disciplines that have to be in play in order to achieve that end result. You have to have a cyber engineer. You got to have someone who understands physical security, and kind of like, maybe Travis, who was presenting earlier, would be the best candidate for it, right? These are physical security, individuals who understand, not traditional physical security, but a lot of them are former military. They carry with them high value or high power weapons. They're, trained in military tactics, and they actually undergo force-on-force type exercises to test and verify that these physical protections are in place. It is its own specialized field. Then you have things like plant operations. These are individuals who sit in a control room and are monitoring all the processes that are happening in the plant. And that takes years to train for. And then on top of that, you have all the different engineering disciplines that are involved, from electrical engineering, mechanical engineering, and all the digital instrumentation and control folks. These are the individuals who are responsible for the design, configuration, and what have you of all the digital components that are a part of these processes. And think about the level of integrity that goes behind that in terms of the way they're configured, because they're making, again, they're sensing or making decisions about, or helping an operator make decisions about how we move large inventories of coolant, or how we redirect certain things within the plant in order to make sure it's functioning smoothly. And it's the plant, and these processes are constantly being tuned. And so someone's out there making sure that the digital components are actually, from a functional perspective, doing their jobs and giving the operators the right decisions to make. And then you have the maintenance folks who are going out there and modifying and configuring and troubleshooting and tuning those components as well. Well, all of that today is cyber, because you can't implement cybersecurity without having at least some knowledge of all of these aspects and be able to work with them in order to implement cyber effectively at a plant. If 80% of all the digital components in a plant are air gapped or otherwise isolated, they can't be connected to, or they can't be touched, they can't be patched. In some cases, you can't even get in physical proximity to them. Imagine if they're in a part of the plant where it's a high level of human risk to even access it, like in a high radiation environment at a nuclear power plant. That means you've got, as a cyber analyst or an engineer, you've got to understand how physical security mitigates and completely mitigates the risk that a cyber threat would otherwise pose to that component. And that's tricky. But now you've got to understand that discipline. But in order to really quantify risks, you got to understand what that component is. You got to understand what process it's supporting. You got to understand the importance of that process to the overall plant operation. And you have to be able to implement mitigation strategies that don't disrupt that operation. In some cases, we have components that, if they were to fail through compromise or what have you, it could shut the plant down, which would cost the plant money. It could disrupt a function, which could shut the plant down and cost money. And worst case scenario, it could hurt someone and otherwise lead to what we might call a catastrophic risk. So what does a cyber expert really look like then in the future, if if we're not necessarily so IT focused, but we got to take all of these other things into consideration. Where do we build this expert? And that's where these partnerships come into play, because in reality, no one organization can do it. So you have universities involved because we're producing the leaders of tomorrow through the university system, the workforce of tomorrow, but we also need private industry involved. This is everyone from the owners and operators of these facilities to the large organizations that support them, like a Raytheon. But we also need the vendors to be involved as well, the Tenables, the PFPs, these types of companies that specialize in cyber in these tough environments. And when we bring them all together, we got to say, look, how do we overcome this problem? Because we have a significant need out in industry for building this workforce. And so ultimately, how do we build them? How do we make someone today who's sitting in a sophomore class at Harvard University who wants to specialize in cybersecurity understand what they're getting into, especially if their future employer is going to be like an Exelon or a Dominion Power? Well, we believe is you need to give them access to what we call an immersion-based environment. You got to put them in a place where they can experience real time what it's like to be out there in these facilities. And you see a picture there of the facility we have in Forest, Virginia. Like I said, that's a full-scale modular power plant. All the industrial control systems and SCADA systems are embedded in. But the nice thing about it is we can break it. Meaning if you go in there and you do something that's invasive and it breaks or it creates an issue, you can easily set back to zero and there's no impact to the operation of the plant. So we can be a little more creative and we can make mistakes in an environment like this, even though the environment is emulating what's happening out there in the rest of critical infrastructure. That's not to say that we are eliminating all the safety issues, because we still have risks. These are still operating components. These are still things that require us to have a high level of due diligence, the same way we would have in a plant. But at the same time, it makes sure that the students understand it. So for example, we would teach students how to give safety briefs before even entering the facility, so they know how to communicate with one another and their teams for things to look out for when they're in the plant, like loose clothing, having the right personal protective equipment, and things like that. Getting to the technology is one thing, but being able to be in these organizations and these environments in a safe way is also equally important, because the risks are a bit higher in that regard. You might have the risk of tripping or otherwise running into something in a data center, but in this facility you could touch something that could burn you. You could hit your head on overhead piping. There's a lot of things that you got to look out for that otherwise you wouldn't have to think about. And this picture gives you somewhat of an example of that. So in the top left corner, that's what we call the component cooling water system. And what that does is you have 4 large industrial pumps, which are pulling water inventory out of a big tank, and we pump that water throughout the lab or throughout the range. And so in this small modular reactor, we pull the water out. So if the reactor were operating and we were producing steam or superheated water, we would need to pull the heat off of those systems. And so just like a radiator in a car, you got to basically push coolant all the way through the system to pull that heat off, and that recycles through. As the hot water comes out, it cools off and then gets pushed back in. Well, that's a massive industrial control system in and of itself. And so a lot of training courses, this is where students can sit and find out, what's working, how is the digital aspect of it, the architecture of it, what can I see, what is it telling me, and how would a threat actor impact that? Because if it were to break, then my whole plant shuts down. At the bottom left, you see the core. That's where we superheat the water. And you'll see different types of instrumentation in there. What does that look like? How do you get to it? How does it communicate? What are the specialized protocols that come into play? And how do we make sure that while we're accessing it, how is it disrupting the operators? What are they seeing? Do we have, the right people in the room with us? So do we need to build, expertise from the engineering group? In other words, do we train engineers to be cyber people, or do we train cyber people to go into engineering environments? Whichever approach we take, you just see that there's a bit of a different type of approach overall that needs to be taken, so that when we get into the environment, we can do what we need to do without posing risk to the plant or to other people. So what if we can't get into the plant itself for whatever reason? Let's say it's operating, it's 140 degrees in there, you don't want to be in there, or we're doing other types of experimentation in that space. Well, that's where the AI-based virtual ranges come in. How can we, through a virtual environment, expose a student to the same types of conditions as they would see in real life, but through a simulated way? And so what we use is these AI-based training grounds where students are immersed into missions, and they have something on the other end that's measuring the level of skill, knowledge, and abilities, and then using that to change the gameplay so that they're progressively moving up in their skill sets. So the key thing is making sure that it's as real life as possible. So scenario building inside of these environments is another key piece. But what's nice is that you can actually access it from anywhere in the world. So you don't have to necessarily put on a hard hat, protective glasses, hearing protection, and composite toe boots. You can sit in the comfort of your own room, dressed any way you want to be dressed, and start learning and understanding how to work in these environments. So what that comes down to is, regardless of whether you have a physical space or a physical lab, or if you have a virtual range, the goal is to get students immersed into these types of environments. And one example was what we were looking at in South Carolina. So what that was is Central Carolina Technical College, for example, and there are other examples throughout the United States. They have a focus on manufacturing. And so they have a manufacturing laboratory where they teach and train students in a 2-year program how to get jobs and to work in technical positions in the manufacturing industry. At the same time, we have Morris College, which is located right there as well, that is building a 4-year program in cybersecurity. So working with someone like Raytheon, one of the nation's largest employers, we started asking the questions: how do we pull these two together so that those who are learning cyber can be in the same environment as the technicians and operators who are going to be going out into the manufacturing field? And can we pull these disciplines together so that everyone is kind of learning in the same environment? Whether you're an engineer who wants to understand cyber, or cyber who wants to understand the engineering discipline, you're doing now that in an academic setting. And the reason for that is because if we think about it, right now, there's about 560,000 jobs that are going unfilled worldwide. And when you think about the things that these employers are looking for, what they believe is that about 36% of all the cyber skill out there lack the skills and experience needed to be effective in their field. Think about that. That's like 1 in 3. But when we were talking earlier about the risks that are inherent to working in these environments, you really don't want the 1 in every 3 people on your team going out into the plant, because that introduces a manifold risk, right? Both to their safety, the safety of others, and the operation of the plant. So what we want to get past is what we believe today is really what we call novice to journeyman level experience in cyber, especially when it comes to working in industrial security. But what's interesting is that about 40% of those in the cyber field have a master's degree. So think about that. Getting through a formal program of study, these students aren't coming out necessarily being able to walk into these environments and be effective. But we think with this immersive level emphasis, the opposite would be true. So if someone goes through our training or someone goes through one of these programs with a participating university, when they go out to interview at a plant or they go out to work at a plant, they're already doing the things that would be expected of them if they were a regular engineer. So they're going to show up with the right type of clothing. They're going to stop and read the signs in the plant so that they don't push a door that they shouldn't push or touch something they shouldn't touch. They're going to have all their protective equipment with them. They're going to be ready to give safety briefs. And when they walk through these environments, they're going to understand how to interpret what's going on and translate what's happening in the field to what's happening in the digital architecture as well. So with that, I'll close it out. But really the main things to keep in mind here is that I think as an industry, and especially for those who are looking to, or either in this industry or those who are looking to get into it, we really need to focus on a more interdisciplinary approach, especially when we're looking at critical infrastructure. And we got to pull industry in to help everyone figure that out. We can't let institutions of higher learning be on their own plane and industry on a different plane and cyber training organizations on a different plane. We all have to come together to figure out what does the workforce really have to have and what do the employers really need, and then build both education and training to meet those needs. And really what that equates to for industrial applications is it's got to be immersive, whether it's in person or a live lab where they're actually touching the equipment, to the virtual ranges that are now available. Use both of them to amplify what a student is experiencing in a classroom environment, and then using that to make them a better product in terms of a future employee, especially given what they're going to face in the world. And so with that, I'll open it up to questions or comments, and hopefully that was helpful.
All right. Hey there, George. Great talk. I don't see any questions in Q&A yet, but we'll give them a minute. If you guys have any questions, why don't you enter them in Q&A or in the Discord channel. And then we'll see if they have any. And then if not, you're all set, George.
Awesome. Well, thanks everyone. I really appreciate being able to spend some time with you today. And, a shout out to CornCon, best conference of the year.
Thanks so much, George. We really appreciate having speakers like you here, and hopefully we'll see you next year.
All right. Thanks.
All right. All right, CornCon Track 2. Next up in about 12 minutes at 10:15, we have Ron Warner, Cybersecurity Instructor at Bellevue University. He's going to give us a great talk on how not to suck at security or how to hack your cyber career. It should be a great talk. See you guys in a few minutes. Please buy some merch in the meantime.